Here, folks, we're going to be doing 0021, understanding the concept of a function, which is very important, probably the most important thing to begin algebra. But as you see, there's a lot, so let's get going right away. Alright, so if we're going to spend all this time talking about functions, we need to know what a function is. And so there's a couple ways to explain it. The most common, or probably the most general, has to do with the fact that it is a set of points, which means you're going to have x values and y values, essentially. And in that set of points, each input, or generally speaking, that's going to be your x value, has a unique output. Okay? So each input has a unique output. So let's look at what that means in a table. So that means if I had these x values 0, 1, 2, 3, and I'll show you a major misconception. Well, maybe first we'll look here. 0, 1, 2, and 3. So if I plug in 0, maybe I get 3. If I plug in 1, maybe I get 4. If I plug in 2, maybe I'll get out 2. If I plug in 3, maybe I get 7. Okay? So that is that table does represent a function. You can see that none of these y values repeat, so that doesn't see. So there's clearly not going to be any sort of problem here. Now, the main misconception, so we'll say this is a function. The main misconception would come from a table like this, where if I said I had 3, 9, 2, 7, 4, 6, and then 5, 9. Okay? So what people do, or people look at this definition and say each input has a unique output, and they focus on unique output and see that there's a 9 and another 9, so they think, hey, that 9 is not unique because it shows up twice, and they'll answer that this isn't a function, but it actually is. Okay? The way the definition works, each input has a unique output. That means that if I had an input of, say, 4, that 4 has a unique output of making something up 5. So that means if this 4 shows up again, and I have like a 6, and I have like 3, 9, something like that. So that means right here, this case, if I plug in 4, I don't just get 5. I get either 5 or 6. And so this point, 4 does not have a unique output. Whereas here, 3 has a unique output, and that output is 9. 5 has a unique output, and that output is 9. Okay? So this guy over here is a function. And this guy over here is not a function. And it's because of this, the 4 not having a unique output. What's nice is it's generally easy to tell from a table because you're looking for this kind of like repeated x value to show you that ambiguity. So that idea of what is a function can be extended to graphs as well. So we'll just kind of sketch a couple of coordinate planes, as you can tell, very neatly and professionally. And so, to just draw a couple things here. Okay, so these are all functions, or I'm sorry, these are all graphs anyway. We're going to talk about whether or not they are functions. And so that definition, if you recall from just a moment ago, is that each input, so each x value, maps to a unique output, which means if I plug in, say, this x value over here, whatever that x value is, if I plug that in, if I look on this graph, there should only be, at most, one place where that is, and it is. So if I plug in this x value, I don't know, make it up, say it was -3, I only get out that y value. Okay? And if I look pretty much anywhere else, that looks like that would be the case. Looking over here, if I plug in an x value here, my y value is here. That's good. If I plug an x value here, my y value is here. That's all good. The problem comes with this third graph, where if I plug in this x value, wherever that is, it maps to this y value and this y value. Okay, and that's a problem. So because we are looking for multiple parts of your function from a single x value, this is typically called the vertical line test, because if you notice, those two outputs fall on that vertical line. So the idea is, if you can go through a function with a vertical line and only ever hit the function once, okay? So here I hit this function twice, and that's bad. So a function like this, even if you don't know what the equation is, this is a function. It passes the vertical line test, which means each input has a unique output. This is a function. And this guy over here is not a function, because it fails the vertical line test. And actually something interesting, if you want to note, on the grid earlier where I was talking about that misconception where if a y value shows up more than once, people think it's not a function. Well, if you look here, like at this y value, it shows up there and there. So there are, in this function here, there's this y value, say like -2 or whatever, shows up 1, 2, 3 times. So it's not those repeated y values that you need to be concerned about. You need to be concerned about the repeated x values, because you need each x value to only map to one point. Super. Alright, so some of these questions are going to be kind of visual as well. So there's one pattern I have in mind, and let me sketch it down for you real quick. Alright, so you might get a picture that looks something like this or nothing like this, but the idea remains the same. And so what they're going to do is they're going to give us, and they're not even going to really ask you, hey, what is the next picture? Because that's almost too easy, okay? Because you'd be able to draw that. They're going to ask you something that you probably wouldn't be able to draw out. So it's like, how many lines are in the 100th picture? Okay. Now, you're clearly not going to sit here and draw out 100 pictures. I know I've said several times that you have tons of time on the test, but you really don't have that much time. Like, let's be serious here. So what you need to do is you need to look for a pattern. So if I look up here, I'll see that it's kind of like a little house shape, and I have 1, 2, 3, 4, 5 of them. So I'm just going to write down a 5 just as my little note. Now with the second one you might think, well, then there's probably 10. But we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's because this guy here in the middle is shared. Okay? So we need to look for a pattern. It's not just going up by 5s. So third one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then our last go over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay? So now we're looking for a pattern between these numbers. And I think it becomes apparent that these are all +4. So that's good. So we have kind of an idea of what's going on. So I could sit here and set n equals 4 and just keep adding 4 until I get to the 100th picture. But that as well is a little annoying. So we maybe want an equation. So I want an equation that will give me the number of lines in a picture based on its number in the sequence. Okay? Now, there's two ways that I could do that. I could start by assuming that there was like a zero, like a picture number 0, which I think is okay to do. So I see here that these all go up by 4, so I could write this to be 4n. So I get 4 times the number it is in the sequence. And then I need to look and see where I'm starting. So if I'm starting with n equals 1, and that should be a 5, if n equals 1, this is only 4, so I'm going to tack on a 1. So y equals 4n plus 1. And that will work out perfectly fine. The other way to do it is to start here and say, well, it goes up by, my first picture is 5, so I'm going to start with it being a 5. And then I'm going to add 4 for every n value that is larger than 1. So I'd be adding 4, but it'd be adding 4 times n minus 1. Okay? And if you were to distribute that and simplify it, you would end up with the first function as well. So either way, if either way makes sense to you, go with that. The top equation is a little bit simpler, so I'm going to use that. And so this final question becomes rather simple. So in the 100th picture, it becomes 4 times 100 plus 1. And so there are 401 lines. And we didn't have to draw a single picture. Pretty cool. Alright, so now this is an interesting new type of function. Distance equals rate times time. So this isn't linear. This isn't quadratic. This is something that's a little bit different. And they give you the distance formula here, so I'm not sure if they would give it to you on the Mtels or not, but that's a good one to know. Just distance equals rate times time. And that's a pretty easy equation to just come up with if you think about just making up numbers for driving 60 miles an hour to go 100 hour or to go 120 miles or something like that. So you can come up with that. I don't think that one's too hard to remember. And so looking at a table, we want to see what this would look like, to look at the relationship between rate and time. So I'm going to just write them as two different letters here, or two different colors. So we have rate times time equals 100. And so if you can see it already, what that means is that since they multiply to give me 100, then that means that so obviously if the rate is like 1 mile per hour, it's going to take me 100 hours, okay? But you can kind of see that as I go faster, it should take me less time. Like that should hopefully be pretty obvious. So let's say this is 4 and 25. I'm just trying to pick numbers that will work out nicely. 5 and 20, the nice little point here is 10 and 10. And then they'll kind of switch back. So I had 5 and 20, now I'm going to have 20 and 5. And I'm running out of space, but you can imagine that now since this 520 is now 20 and 5, that then I would have 25, 4, 52, and 101, meaning if I went 100 miles an hour, it would only take me 1 hour. And so what on earth does this look like? So if I had this is how long it's going to take me as I travel faster. And you see, if I go 1 mile an hour, I'm way up here at like 100. And then at 2, I'm literally like half that. And then at 4, I'm half that. And you see this kind of like curving. And what I have is this function that looks something kind of like this. And on the ends here, these are what are called asymptotes, meaning that as I get closer to a rate of 0, my time will go up forever and never touch this line. And then as my rate goes on forever, my time will go down, but it'll never touch there. So that means if I was actually going like half a mile per hour, it would take me 200 hours, so it'd be way up here. Or if I was going 200 miles per hour, it'll only take me half an hour. And you can see that you'll never get there instantly, and as long as you're moving, it'll never take you forever to get there. So what we have is this is called what we could say here is that R and T are inversely related. So this is an inverse relationship between these two values. Okay, and what that means is very simple. It means that as, let's say, my R value goes up, so as my rate increases, my time is going to decrease, or vice versa. So that means as my rate decreases, then my time is going to increase. Okay? And so that just means that as one variable changes, a second variable changes in the opposite direction, and that's an inverse relationship. Okay? If there were a direct relationship, you could imagine something with a direct relationship. As one variable increases, the second variable increases as well. As the first variable decreases, the second variable decreases as well. So they go at the same point. This is a very cool graph. A qualitative graph is basically a graph that doesn't have any numbers. It just kind of physically represents objects or people. And I'll be perfectly honest, I've really never seen another graph like this, aside from this one that I found. I think this one is fantastic. I haven't found any others, really, so I don't know how likely it is that this will be on the test. But real quickly, I'd like to show you kind of how we'd go about doing this. So you see here, you aren't given any values for these people. You're just given any quantitative values, like height or anything like that. You're given qualitative values, like you can actually see how tall they are, and you just say that they are young or teenage or older, okay? And so what it is we have to figure out which one of these people are on this graph. And so this is a graph for height, so the people down here are the shortest and the people up here are the tallest. And this is the graph for age, so down here represents the youngest and up here represents the oldest. So to get an idea of what's going on, we'll do the easy one first. So if you look over here at our buddy Gavin, Gavin is only yay tall, so he is by far the shortest person, and he is the youngest person. He's the only person labeled as infant. So if you look here, we're looking for somebody who is very low on the scale of age, and somebody who is very low on the scale of height. And so you could imagine that this right here is our buddy Gavin, 7. So Gavin is number 7. Okay, and we'll kind of go from there. So you can either try to follow the map via height, okay, or follow the map via age, okay? So if we were just going to go by age, we got rid of the infant, and if I'm following up this axis of age, I see 7 and then 6. So I need the next youngest person, okay? So I have a young woman, teenage boy, older man, young girl, teenage girl, older woman. Okay? So I have young woman, I have young girl. A young girl sounds younger, but just to make sure, let's look at height as well. So this person is also not only the second youngest, but also the second shortest. And as you see here, we have, if I drew kind of like a line across here, you'd see that Kathy is definitely the second shortest. So I believe she is our best contestant to be number 6. So Kathy here is number 6. Alright, so now moving up, we have something we need to be concerned about here, because we have 4 and 5 as far as age is concerned being the same. So I have young woman, teenage boy, older man, teenage girl, older woman. This is the only name that shows up twice, teenage. So we have teenage girl and we have teenage boy. So now which one is 4 and which one is 5 when these ages are equivalent is we need to now look at the height. So out of 4 and 5, which have the equivalent age, 5 is taller, 4 is shorter. So if I'm looking at Brenda and Errol, I'm going to say that Brenda is the shorter one, so she is 4. Errol is the taller one, so he is going to be 5. Okay, you can kind of see how this goes. If I'm going to continue looking at age, I'm now up at number 3, who's all alone. So we have young woman, older man, older woman. Older and older should match together, so they're going to be my 1 and 2, which means our young woman here is going to be number 3. Whoops, that's a different color. Oh well, too late now. So last guy here, finally up on age. 1 and 2 are 2 oldest people. We have older man, older woman. And same kind of tiebreakers before. 1 is shorter, 2 is taller, because we have to follow this kind of height axis down here. So our shorter person is actually Dennis here. Dennis is the short guy, so he is going to be number 1. And then Alice is our very old, very tall woman, and she is number 2. Okay? So you really just have to kind of go about this looking at it from one qualitative aspect. Okay, so like I went through as age, and then when there were ties, I had to use height as kind of a tiebreaker. And no matter what they give you, I imagine that you'd probably be able to use a very similar strategy on it. Okay. All right, next thing we're going to be talking about is a little bit of geometry and measurement. As you see here, another long list of stuff to get through. Geometry is kind of like several whole courses, so I guess we're going to try to make this quick. Alright, so these will probably be one of the most straightforward geometry problems that you'll run into. And that would be a kind of combined shaded area problem. So you have to forgive how poorly this is drawn. It's essentially supposed to be a rectangle with side lengths of 5 and 6. And then if you can imagine sitting on top of it is a kind of a semicircle. Okay? So there's no like formula for this particular shape. So they're going to have you break it down. So to find the area of this, it's going to be the area of the rectangle plus the area of the semicircle. Okay? So these are formulas that you're going to definitely want to know. The area of a rectangle is length times width. And then the area of a semicircle is, well, I don't know. Well, the area of a circle is pi r squared. And so if it's a semicircle, it is half of a circle. So it's going to be 1/2 pi r squared. Okay? So I'm going to look here. We have, we clearly have in this shape our rectangle. A length of 5, a width of 6, so that's going to be good. So this is going to be 6 times 5. That's not too bad. It's going to be 1/2 pi r squared. If you're, what is our radius? So if I look here, if this is a rectangle and that length is 6, then that also tells me that this length is 6, meaning that all the way across that circle is a length of 6. So if I wanted to know halfway across that circle, that guy's going to be 3. So our radius of our circle is 3. Okay? And now we just need to simplify this. This is going to be 5 times 6 is 30, plus 1/2. 3 squared is 9. 9 times 1/2 is 9 halves. So plus 9 halves pi. And without a calculator, that's really the best you're going to do. Pi is a little bit above 3. So if you wanted to, if they needed you to estimate it, like they're approximating the area, then that would be 30 plus. I probably wouldn't use a fraction if I was estimating. So 9 divided by 2 is 4.5. Okay? And then pi is a little over 3. So pi is 3.14. And so without actually writing anything down and scribbling, 3 times 4.5 would be 9, 13.5. So you're looking at 13.5 plus 30 is 43.5. But pi is actually 3.14 and not 3. So, I don't know. I would say, without doing any work, that it's about 44. And it is important, I suppose I don't have any room in here, that whatever it is units squared. Okay? Because we're measuring an area, everything is in square units. Alright, these are all conversions that I think any test that somebody's giving you would expect you to know. So we have kind of our conversions between our nice US metric here versus those crazy Europeans that came up with this system, which is infinitely easier and makes significantly more sense. But then again, this is where we are, so you got to know those things, unfortunately. And it'd be a conversion problem. So they might say, convert the speed 7 miles per hour to feet per second. Okay, so converting 7 miles per hour to feet per second. So the way we're going to do that is we're going to multiply. We're going to use equivalent ratios. So 7 miles per hour is the ratio of 7 miles traveled in 1 hour. Okay? And our goal is to multiply this by a bunch of equivalent ratios. So ratios where the numerator and the denominator are equivalent, meaning we're multiplying really by the number 1, which is not going to change our value. Okay? So maybe the first and the easier thing would be, hey, I have something with a denominator of hours. I want it to have a denominator of seconds. So I have to do a little converting. So we're going to multiply this by something that will eliminate hours. So if I have the ratio of 1 hour, I'm trying to convert it down to seconds. So I don't know how many seconds are in an hour, but I do know that an hour has 60 minutes. And so because 1 hour and 60 minutes are equivalent, I'm not changing anything. I'm not changing the value, I'm just changing the way it looks. So we're still at minutes, so I know that 1 minute is equivalent to 60 seconds. Okay? So as you can see here, we've basically reduced with the hours. So this is 1 hour over 60 minutes, 1 minute over 60 seconds. So if I were to multiply everything across, what's going to happen is hours is going to cancel with hours, minutes is going to cancel with minutes, and my solution will be in miles per second. Okay? But that's not even quite where I want. I want to be in feet per second. So I also have to multiply by something to get rid of this miles. And if I have miles in the numerator, I'm going to want to multiply with miles in the denominator. And those are going to reduce. So I know that 1 mile is equivalent to 5,280 feet. Okay? And now when I multiply, miles reduces with miles, and I'm going to end up with something where my numerator has the units of feet, my denominator has the units of seconds, and that's exactly what I wanted. Okay? To save out all the long multiplication, you would end up with, so 7 times 5,270. I've done this off to the side. This ends up being about 10.27 feet per second. Okay, super. And any unit conversion, you do basically the same thing. Sometimes it's called unit analysis, where you want to make sure that if I have hours in the denominator, I have hours in the numerator, miles in the numerator, miles in the denominator, etc. Because you want everything to reduce and leave you only with the units that you would like. And you can extend this idea to really a bunch of things. Alright, and sometimes they're going to throw really weird things at you for area or volume or something like that. And so, first off, we need to know the basic formulas. So if I was looking for the area of a square, I'll try to make these as neat as I can. The area of a square is just side squared. If we wanted a rectangle, okay, so this is a shape where it's like a square, but the two sides aren't necessarily the same. This is length times width, and you can see that clearly works for square as well. It's just the length and width would be the same. And so we have a circle. Circle is pi r squared. That could show up a lot, especially on a non-calculator test where they'll want you to approximate area. And so you have to know that pi is about 3.14159265535. Anyway, a trapezoid forgiving the 2-year-old handwriting. A trapezoid is interesting. The trapezoid is 1/2. Whoa, hold on. We're moving everything around here. Trapezoid is 1/2 the height times the sum of the bases. So this is B1 plus B2. Okay? And so what that is referring to is if I had a trapezoid and it would look like something like that. The bases are the parallel sides. Like this would be one of the bases, this would be another base, and then the height would be that distance right there. So the bases would be the parallel sides. And the last one would just be the area of a triangle, which is 1/2 base times height. So that brings me to this example. Let's find the surface area of this dice if it is 8 equilateral triangles with a side length of 2 centimeters. Okay? And so the surface area for here, I'm going to say that this is going to be 8 triangles. Okay? And I'll write that out masterfully like that. Which means that our total surface area is going to be 8 times the surface area of one of those triangles, or the area of one of those triangles, 1/2 base times height. Okay, so we need to figure out what is the base, what is the height of this triangle. Well, all of my side lengths are 2, so this is 2 and 2. Property about isosceles triangles. Because these sides are the same, 2 and 2, this height is actually going to bisect the side that it's drawn to. So this height is actually going to cut this side in half to 1 and 1. Okay? And then this triangle that is formed, if I'm looking for the height, is actually a special right triangle, because this is a triangle where it's 30 degrees, 60 degrees, 90 degrees. But if you're not familiar with the sides of a special right triangle such as that, you could just use the Pythagorean theorem, where I don't know the height, so I have 1 squared, because that's a leg, plus my height squared, because that's the other leg, is equal to 2 squared, because that is my hypotenuse. And so that's going to give me h squared is equal to 4 minus 1. So h squared is equal to 3, which means my height is equal to the square root of 3. And so I'm going to be left here. I'm going to have 8 times 1/2 is 4. My base, my entire base, is 2. And my height is root 3. And that's going to give me a total of 8 root 3 centimeters squared. Okay, so any problems that you're dealing with, especially when you're looking for surface area on 3-dimensional figures, break it up into its 2-dimensional shape. So I didn't draw 8 of these triangles just because I knew that they would all be exactly the same. They would all be exactly the same. If they were going to be different sized triangles or rectangles or something like that, I would have drawn each separate shape out. These questions will almost certainly be on the test because they are, I think they're very cool because they show an understanding of, really, I think it shows a lot of number sense and a lot of understanding of the formulas to know how changing one side of a shape will change the area or the volume or something like that. So if you double the height of a triangle, the easiest way to answer these questions is by just actually trying numbers. So like find the area of a triangle with a height of 5 and a base of 2 and then try it again with a height of 10. Okay, like actually doubling it. The way that I would do it, which is not to say that's a bad idea, but the way that I would do it is I would have that the area of a triangle is 1/2 base times height. Okay? So I'm going to say, well, if I'm just going to let the height be x, then my area is 1/2 base times height. Or I'm not even going to use it a variable. I think that's going to be confusing. So here, so that is our area with a height. So now if I double the height, okay, then my area is going to be 1/2 base times, and then twice my height, doubling my height, is 2h. And so when I multiply and I distribute, 1/2 times 2 is 1. This is going to be base times height. And you can see how do these two equations compare. The second one is double, so the area doubles. So when I double the height, I double the area. You say, well, duh, couldn't you have seen that coming? So, well, yeah, I suppose. But now how to answer a question like this, where maybe it's not as obvious. Because tripling the side length of a square is not going to triple the area. Okay, so the area of a square is just side squared. Now if I were to triple the area of a square, my side that I'm squaring is not s. If I'm going to triple the side length, this side length is now going to be 3s. Okay, and if I'm squaring something, I'm multiplying it by itself. So 3s times 3s, 3 times 3 is 9, s times s is s squared. And as you can see, how do these compare? The area is 9 times larger. Okay, so you want to be careful, but using an example will always work out for you. So if you're not just going to use the variable and then just see how they compare, try the area of a square with a side length of 2, and then try the area of a square with a side length of 36, and get your answer that way. Okay, so here we are. We're going to change some rates here. So you have two different rates. We have our rate where we are going downhill. So we're going downhill 500 feet in 30 seconds. And then we have our rate once we hit the bottom and are no longer going downhill, where we're going 300 feet in 20 seconds. And so the average speed for the entire trip, I'll tell you what people will do wrong, is what they will do is they'll find the speed going downhill, they'll find the speed going flat, and then they will average them. They will just add them up and divide by 2. And the reason why that's not going to work is because that assumes that you do those things for the same amount of time. It assumes that they're proportional. So the best way for me to kind of convince you otherwise is, and actually this is a strategy you should take on yourself, is look at extremes. So like really exaggerate what's going on to see if what you're doing makes sense. So if I said I was going downhill, an average of, say, 30 feet per second, okay? And I was going down that hill for 3 seconds. Okay, so for a very short amount of time I'm going down that hill. And then I said that I was going to coast for an average of, for 10 feet per second, for a very long time. So that was 3 seconds. Let's say this was for 100 seconds. Okay? So for a very, very long time afterwards, I'm going 10 feet per second. My average speed for the trip is not 30 plus 10 divided by 2. So my average is not 20 feet per second, because this guy was only for a very short period of time. This guy's for a very long period of time. So hopefully you can see that my average is going to be a lot closer to the 10 feet per second than it would be to the 30. It's definitely not going to be 20. It's definitely not going to be right in the middle. So the best way to look at this is to not look at it as part of a trip. You want to look at total distance. Okay? So going downhill is 500 feet in 30 seconds. Okay? And then we're coasting at 300 feet over 20 seconds. Which means that in total we have traveled 800 feet, right? So we've gone 500 plus 30, 800 feet, a total of 800 feet in a total of 50 seconds. And that is going to come out to a very nice number of an average of 16 feet per second, okay? So you don't even really have to do any crazy ratios or anything. You just look at total distance, total time, and that will give you your average rate for the entire trip. Alright, we're going to have a couple of things for you guys this week. There's a lot that's going on this week, so I'm not going to really give you any additional work to do. Really, just try to familiarize yourself with the area formulas. Area formulas, maybe some volume formulas. Find those online, because those are going to be very useful. And just your familiarity with formulas like that is going to make things very quick, because we're going to be doing a lot of geometry. So we're almost done, and I'm not going to give you any little examples to work on. Thank you for watching. Goodbye.